Have you ever wondered exactly how environmental regulators manage to track down microscopic, highly hazardous gas leaks hidden inside massive industrial complexes while you are in the right place? Welcome to this explainer, where today we're decoding EPA Method 21, and we're going to take you on an inspector's actual journey to hunt down unseen industrial emissions. Let's dive right in.
So think about it. How do you catch a dangerous gas that you literally can't see? It really is the ultimate detective mission. Inspectors have this massive task of locating highly flammable and sometimes incredibly toxic volatile organic compounds, we usually just call them VOCs, long before they can do serious damage to the environment or, to human health. We're talking about chemicals like benzene or methyl alcohol. These things can act as severe fire hazards or serious tissue irritants. And because these gases are often completely invisible to the naked eye, catching them requires a very, very specialized approach.
To really master this methodology, our explainer today is going to follow the exact procedural steps an inspector takes out in the real world. We'll hit defining the threat, safety and gear, tuning the instrument, field tactics, and finally, a pretty surprising low-tech backup called the soap bubble alternative.
All right, Section 1, defining the invisible threat and where VOCs hide. We have to start our mission by understanding exactly what we're hunting. Modern industrial facilities, as you probably know, feature massive networks of process equipment. We aren't just looking at, say, one big exhaust pipe. We need to check a frankly overwhelming number of potential leak points. This covers everything from everyday valves and flanges to those massive heavy-duty pumps, compressors, and pressure relief devices. Basically, anywhere two pieces of metal join together, or where a moving shaft enters a casing, a truly microscopic gap can form. And that right there is exactly where these volatile organic compounds manage to slip through.
Moving on to Section 2, safety and essential gear, and why it absolutely must be intrinsically safe. The prep work here is intense. You can't just walk into a hazardous environment with some off-the-shelf electronics. Because VOCs like heptane or benzene are severe fire hazards, our primary weapon has to be a highly specialized portable VOC monitor. Now, these instruments usually rely on advanced detection methods, things like catalytic oxidation or flame ionization. But here is the absolutely critical part. The device must be certified as intrinsically safe. That means the electrical circuitry is specifically designed so it literally cannot produce a spark powerful enough to ignite an explosive atmosphere. In EPA terms, it has to meet Class 1 Division 1 conditions. I mean, you're carrying a sophisticated chemical sniffer into a potential bomb, so your gear absolutely cannot be the trigger. But wait, before we start measuring anything, we need to know our exact threshold for danger. What actually counts as a leak? That's defined by a critical metric called the leak definition concentration. The EPA doesn't just vague post and say find a leak. No, they specify a precise parts per million number based on a reference compound, like methane. So, if the local concentration right at the surface of a valve hits that specific number on our calibrated meter, boom, we officially have a leak on our hands.
Which brings us to Section 3, tuning the instrument through calibration. Just like a musician meticulously tuning up before a high-stakes concert, an inspector has to calibrate their gear.
Since the data collected here is legally binding, the machine's accuracy is totally non-negotiable. We have to make sure our instrument correctly translates the invisible gas it smells into accurate, actionable data. And it does this using what's known as a response factor. Essentially, it's just the ratio between the actual known concentration of the gas in the air and the number the machine spits out on its screen. Now, the really crucial point here is that this response factor must be less than 10 for every individual VOC we measure. If that response factor is too high, the machine is basically blind to that specific chemical, meaning dangerous leaks could go completely undetected. Keeping this factor under 10 guarantees our readings stay highly reliable across a wide variety of toxic gases. So let's look at how this builds into the precision check. It's a strictly regulated, four-step math routine performed before the analyzer ever goes into service. First, you introduce zero gas, which is basically perfectly clean air with almost zero VOCs, just to baseline the machine. Then, you introduce your known calibration gas. You do this whole cycle 3 times, calculate the average algebraic difference, and then figure out the percentage of variance. Think of it as a rigorous stress test for the sensors.
And the EPA enforces a really strict quality control mandate right here. That final precision percentage, it must be equal to or less than 10%. If your machine is off by more than that, it outright fails. You cannot use it. You literally have to recalibrate or repair the device before taking a single official reading. No exceptions. Speed also matters a lot. We run a response time test where we quickly switch the probe from zero gas to the calibration gas. According to Method 21, the instrument must reach 90% of its final stable reading in 30 seconds or less. When you're out there surveying thousands of valves in a sprawling refinery, you simply can't wait 5 minutes for your machine to process a single sniff.
Okay, so we've got our essential safety gear, our instrument is expertly tuned, and it's passing all the precision checks. We are ready. But before we head out into the field to hunt down those invisible leaks, take a quick second to calibrate your own screen by hitting the subscribe and like buttons below. It really truly helps us keep these deep dive explainers coming straight to your feed.
All right, Section 4, Field Tactics, Hunting the Leak. Gear in hand, we finally step out onto the industrial floor.
It's a loud, complex environment filled with massive steel structures. Now, the EPA document splits our field tactics into 2 specific methods depending on the regulation. Type I is a direct hunt for the maximum concentration. You're putting the probe right up against the metal. Type 2 is a bit different. It's designed to prove there are no detectable emissions. For Type 2, the inspector actually first measures the local ambient air about 1 to 2 meters away from the source to get a baseline. Then they compare that baseline to the reading right at the surface of the equipment. If the difference is practically zero, it's considered clean. Now, for specific equipment like valves, the inspector executes what we can call the sweep technique. They physically place this tiny probe, we're talking no larger than 1/4 inch in outside diameter, exactly at the interface where the valve stem exits the packing gland. Then, they slowly trace the entire circumference, just watching that meter for any spike. If the meter jumps, they stop right there and sample that exact spot for twice the instrument's response time, just to ensure they capture the absolute maximum concentration. It is incredibly meticulous work. Which brings us to our final section, Section 5, the soap bubble alternative and visual screening. So, what happens if you need a lower tech, completely visual method to spot a leak? After all that talk about precise calibration gases and intrinsically safe electronics, the EPA actually offers a dramatically simpler fallback. It's called the alternative screening procedure. An inspector can literally take a squeeze bottle, spray a simple concentrated detergent and water solution over a pipe connection, and just watch. If a VOC gas is leaking out, it will literally blow soap bubbles. If no bubbles form, the source is presumed to have no detectable leaks. Kind of amazing, right? However, this analog backup has some pretty strict rules. You cannot use the soap bubble method on equipment with continuously moving parts, like a rotating pump shaft. You can't use it if the surface temperature is below freezing or if it's above the boiling point of the soap solution, and obviously it won't work on large open areas or if the equipment is already leaking liquid. If any of those conditions exist, you are forced to revert immediately back to the high-tech instrument survey.
Going through EPA Method 21 really makes you think, doesn't it? We walk around completely unaware of this meticulous, highly technical detective work happening behind the chain-link fences of industrial facilities, all to capture dangerous gases before they ever reach us. It leaves you wondering, if this level of rigor is required just for a single factory valve, what other, unseen, strictly regulated procedures are quietly protecting our everyday environment? Thanks for joining me on this explainer, and keep your curiosity calibrated.